Hi class, this is Mr. Morris, and we're talking today about limiting and excess reactant problems. You've seen a little bit of this in the introduction to stoichiometry, but we want to go into a little bit more detail on how to solve word problems involving mole stoichiometry with limiting reactants. This is when you're presented with amounts of multiple reactants. So let's get started. When you have multiple reactants that are given, so more than one amount of reactant, we have to determine which reactant will be all used up and which will be left over after the reaction is completed. The reactant that will be all used up, in other words, the reactant that will run out first, is called the limiting reactant. Okay, this reactant is called the limiting reactant because this reactant limits the maximum amount of products that can be produced. If you think about maybe making a grilled cheese sandwich, for example. If I have 4 slices of bread and 3 pieces of cheese, well, with 4 slices of bread, I can only make 2 sandwiches. If I have 3 slices of cheese, I could make 3 sandwiches. Well, which one limits me? Well, the one that can only make 2 sandwiches. So I'm limited by bread, by having 4 slices of bread. So I'll have 1 leftover piece of cheese. That's the general idea that we're talking about, but we're going to do this with chemistry. The reactant will be left over. In other words, the reactant that will be in excess is called the excess reactant. The excess reactant, that's that word right there again. The amount of excess reactant is also usually asked for. So we'll usually be solving for the amount of excess reactant remaining. I'll teach you how to do that. Okay, let's consider this reaction below. We've got 1N2 plus 3H2 yields 2NH3. We learned balanced reactions in the last unit. But those coefficients have a meaning. We want to make sure that we understand what that meaning is. Remember, that's the number of moles of reaction, the number of moles of nitrogen that can react with 3 moles of hydrogen and 2 moles of NH3. So we're going to complete the table below using the balanced equation and give the amount of reactant used, or in other words consumed, or the amount of product that's produced. And note that when both reactants run out at the same time, if both run out at the same time, we're going to put both as the limiting reactant and none for the excess reactant. That's because there won't be any left over. Okay, so let's start with part A here. If I have 2 moles of N2 available and 6 moles of H2 available, compare that to our reaction. Well, with 2 moles of N2, I can create 2 batches. I could do the reaction twice because that's twice what my reaction, or you could say my recipe, calls for. Okay. All right, now let's look at this number, the 6 moles of H2. Well, 6 is 2 times as much as 3, so that means I can make 2 moles of the reaction based on hydrogen. So I have enough nitrogen to make 2 batches and enough hydrogen to make 2 batches. That comes out to be the same number. The number of batches that will realistically happen is 2 because it's the same number for either case. The amount of N2 that is consumed, well, if I have 2 batches and each batch is 1 mole of N2, 2 of those batches will consume 2 moles of N2. Let's put units there. 2 moles of N2 will be consumed. Okay. If I have 2 batches of H2 and each batch has 3, 2 times 3 would be 6. 6 moles of H2 would be consumed. All right, the amount of NH3 produced. Well, if I produce 2 batches of NH3, it means I made 2 times 2. That gives me 4 moles of NH3 that are produced. So I'm just taking the number of times the recipe is run, the number of batches, and multiplying that by whatever coefficient we're talking about. And then our amount of excess remaining, well, we didn't have an excess reactant. They were both completely used up. I started with 2 moles of N2. I ran out. I started with 6 moles of H2. I used it. I used all 6 moles. I ran out. What's the amount of excess remaining? None. Or you could say 0 moles. So for part A, scenario A, there is no limiting reactant. Okay? There's also no excess reactant. This ratio of reactants is called the stoichiometric ratio. Okay? In a stoichiometric ratio, they are perfectly balanced. Okay? So that both reactants run out. We're going to run out of both reactants because it's perfectly balanced. There's nothing left over. Let's look at part B. 5 moles and 6 moles. So if I have 5 moles of N2, that's 5 times what the coefficient is. So that means I can make 5 batches. Okay? That's the N2. Now let's look at the H2. I have 6 moles of H2. Okay? That is twice the number 3, right? It's 2 times as much as the recipe calls for, so I can make 2 batches. Okay, how many could I realistically make? Well, I couldn't make 5. If I tried to make 5, I would run out of hydrogen, so I can only make 2. Realistically, I can make the smaller number. Just like in a sandwich metaphor that we used, we can realistically make the smaller number of sandwiches. The nitrogen that is consumed. Well, if I can only make 2 batches of this recipe would be 2 moles of nitrogen. Okay. 2 batches of hydrogen, 2 times 3 is 6, that would be 6 moles of hydrogen. Okay, the amount of NH3 produced, well, it's 2 batches. 2 times 2 gives us 4 moles of NH3. And the amount of excess that is remaining, well, what was in excess? What did we have extra? We used all of the H2. What's left in excess would be the N2. I had 5 moles of N2. I only used 2 moles of it, so 5 minus 2 gives me 3. 3 moles of N2, that's my excess. Look at part B down here. In scenario B, the limiting reactant is H2, and the excess reactant is N2. At the end of the reaction container should contain what? Now this is the part where you kind of do a little bit of thinking. After this reaction has happened, I should be making product, right? My limiting reactant is all used up, but excess means it's left over. So what I should have in the reaction vessel, after the reaction has occurred, I should have product and excess. Our product is NH3. Our excess reactant was N2, so I should have NH3 and N2. Look at scenario C, 2 moles and 8 moles. So 2 moles of N2, that gives us 2 batches. 8 moles of H2, we're going to have to do a little bit of math here. Because 3 doesn't go into 8 a nice number of times. So I'm just going to divide it. 8 divided by 3, that tells me I can make 2.67 batches. Okay, what number of batches would realistically happen? It's the smaller of the 2 numbers, so that would be 2. The number of moles of N2 that are consumed, well, 2 moles. You notice this is 2 batches again, so I can really do the same numbers, okay? Moles of H2 that's consumed, 2 times 3, that's 6 moles. are consumed, and 2 times 2 gives us 4 moles of NH3 being produced. What about the excess reactant remaining? Well, I've got 8 moles at the beginning. I only used 6 moles, so 8 minus 6 gives me 2 moles left over. 2 moles of what? 2 moles of H2, the excess reactant. So in scenario C, the limiting reactant is N2, excess is H2. At the end of the reaction, what should we have? Product and excess. So in this case, we should have NH3 and H2. Notice that the number of realistic batches is equal to the number of batches of the limiting reactant. It's the smaller number. The number of batches of the limiting reactant is the smaller number of batches for the 2 reactions. And then this word batch, we don't really use that in chemistry. I'll use it kind of to remind you what this is, but the technical term, the chemistry term for a batch is mole of reaction. MOL RXN is usually how it's written. That comes up a lot more in AP chemistry, but it's a useful term to know in pre-AP chemistry as well. On the next page, we're going to go a little deeper and learn how to solve these in word problem form.